Everybody, and welcome to Theorem 9.1. We are looking at page 69 of the workbook. This is called the normal subgroup test that we're about to talk about. Okay, so recall what we just talked about in the previous video. We introduced the definition of what it means for a subgroup to be normal in a group. We talked about how a subgroup being normal has the nice property that when you look at its cosets in the group, those cosets actually form a new group. Okay, so it would be useful to know when we have a normal subgroup to be able to look at a subgroup and tell if it has this property of being normal. That's what Theorem 9.1 is about. Okay, let's take a minute just to read this together. So it says that a subgroup H of G is normal in G if and only if this condition is satisfied. X times H times X inverse is a subset of H for all X in G. Okay, now where does that condition come from? We can maybe get a little bit of insight into that just by reminding ourselves what the definition of a normal subgroup is. Remember, it was about left and right cosets always being equal. In other words, being able to say that those two cosets are equal for any X in our group. And if you kind of just take that statement and algebraically play with it a little bit, if you multiply both sides by X inverse, here's what you would get, just kind of symbolically. Okay, the X and the X inverse on the right-hand side would cancel out, and notice that this statement looks an awful lot like what we have here. Okay, that's really what makes this theorem work. Now, to rigorously prove it, we'd have to do a little bit more than that, but that's kind of the basic gist of it. Okay, and then I want to mention that there is an equivalent way of restating Theorem 9.1 that's convenient. Okay, and this is what we'll focus on mainly when we're proving that a subgroup is normal. So equivalently, H is normal in G if and only if the product X times H times X inverse is always in our subgroup for every X in G and every H in H. Okay, that's a condition that we can use to show that a subgroup is normal. Okay, now we could prove this theorem. I'm going to actually skip over the proof in this video and just make the comment that if you're interested in the proof of Theorem 9.1, you could just see the written notes. Okay, there's a proof there. Okay, what we're going to do in this video is to move on to example 2, down at the bottom of the page here, and just demonstrate how we can use Theorem 9.1 to show that a subgroup is normal. All right, so let's scroll down. We may need to scroll back up in a minute. Just read example 2 together here. So they'd like us to show that H is a normal subgroup of GL2 of R. Now, it's been a while since we talked about that set, so let's maybe remind ourselves what that means. GL actually stands for general linear, and this is a group of matrices. In particular, it's the group of invertible matrices that are 2 by 2. Okay, I'm just going to write that in words. Okay, with entries in the real numbers. Okay, and so the set H that they're talking about here is the set of all matrices that are in that set. So we're talking about invertible 2 by 2 matrices that also have this property. Their determinant is equal to 3 to the k for some integer k. Okay, let's see if we can show that H is a normal subgroup. What would we need to do that? Okay, well, technically there would be 2 steps. Okay, so first, we would have to show that H is a subgroup at all. Okay, so we'd have to show that H is a subgroup of G. Okay, and I keep saying G. I really mean GL2 of R. That's the group that we're talking about. Okay, I'm going to leave this to you. This is an exercise that we've done earlier in the course. Okay, so I'd like you to think about that step of just showing that it's an ordinary subgroup. Okay, and once we know that it's an ordinary subgroup, then we can show that it's also a normal subgroup. Okay, so show that H is normal in G. That's the part that I'd like to do in this video here. Okay, so what we're going to do is to use, let me see if I can get this back into the picture here, we're going to use this note that we mentioned up here. Okay, so what we need to show is that for any x in our group and any h in our subgroup, that this product, x times h times x inverse, lives in our subgroup. That's the strategy that we're going to use here. So we'll start by taking any h in our subgroup and any x in G, okay, which is GL2 of R. Okay, and actually, I see that I'm using G on you again, so let's just make a note here. Whenever I write G, I really mean GL2 of R. Kind of a generic notation for our group. Okay, just so that this doesn't get too confusing here. Okay, so we've started out by kind of choosing these two elements, looking back at the top of the page here. Now we need to look at this product and show that that's in our subgroup. Okay, let's make a note of where we're going with this now. Okay, so to show x, h, x inverse is in H, and remember what it means to be in H. It means that that product has to have this property. Its determinant has to equal 3 to the k for some integer. Okay, so that's where we're going to try to go. All right, so the first thing that we want to do is just make the observation that because we chose this h to be an h, we know that the h does have that property. Its determinant does have to be 3 to an integer power. Okay, so we'll maybe start by making that observation just to get the ball rolling here. Okay, there exists a k in Z such that the determinant of h equals 3 to the k. And with that observation, we are ready to look at the determinant of x inverse and to see if it has the property that we want it to. Okay, and actually, I just noticed I've used the variable k twice. Okay, so maybe just to avoid that, might be better to call that something different. So maybe 3 to the j, just so that that j is not the same as the k that we have here. Okay, so let's see what happens if we look at the determinant of x inverse. Okay, well here, we need to use a fact from linear algebra, okay, and that is that when you take the determinant of a product of matrices, that's equal to the product of the determinants. Okay, so this is equal to the determinant of x times the determinant of h. And then one other property says that when you take the determinant of the inverse of a matrix, it's equal to 1 over the determinant. Okay, so on that line, I used a bunch of linear algebra facts, and I'm just going to mention that here. Okay, and then we look at what we've got, and if you think back to determinants, it might have been a while since you've done one of these, but taking the determinant of a matrix gives you a scalar, it gives you a number. And so even though x and h are matrices, these determinants that we have here are just real numbers, okay, which means that we're free to change the order around if we want to. We're just talking about real number multiplication here. So we are perfectly free to switch the order of the last two terms and rewrite it like this. And then to notice that what we're doing here and here, we're just taking a real number times 1 over a real number. It's like kind of maybe taking 2 times 1 over 2. We're going to get 1 if we do that. Okay, so what we get then, if we put that all together, is just 1. Whoops, let me be consistent with my colors here. Okay, that's 1 is what you get when you take the determinant of x times 1 over the determinant of x times the determinant of h. But what was the observation that we made about the determinant of h above? It's equal to 3 to the k. Okay. And so if you look at what we did, we showed exactly what we wanted to, and that is that the determinant of xh x inverse is equal to a power of 3 to an integer power. We have just shown then that xh x inverse is indeed an element of our subgroup. Okay, and so by theorem 9.1, H is a normal subgroup. H is normal in GL2 of R, and we are done with our proof.